All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for AP Chemistry. And we're moving through Unit 3, and we're going to pick up by looking at phase diagrams within our intermolecular forces unit. And so we've spent the first couple of videos looking at intermolecular forces. We started looking at properties of liquids in the last video, and we started looking at this idea of vapor pressure and how we can talk about how liquids go to gases. And we even looked at phase changes and energy associated with that. So phase diagrams are a tool that chemists can use to look at the various conditions at which a substance will exist as either a solid, liquid, or a gas. That's ultimately what a phase diagram is going to do. So let's just dive right in. So this shows the relationship between the three phases of matter at various temperatures and pressures. And that's a really key piece. It's going to show us this relationship at differing temperatures and pressures of our substance. Now, here is an example of a phase diagram. Now, very generic, but notice that on the y-axis, you've got pressure. And then notice on the x-axis that you've got temperature. Now, when you look at this diagram, I'm going to talk through all the different components that you see, right? So notice that you've got the three sections that are kind of different colors. You've got the solid section, the liquid section, and the gas section. And notice that they've been nice enough to show you particle level representations of a solid, of a liquid, and of a gas. Okay, that's the first thing I want you to kind of take notice of. The next thing that I want you to take notice of is that they've got this line, or these series of lines or curves, if you will, that are separating all the different segments of those phases of matter. Now, notice that essentially what I'm going to call segment AC or CA, every point on that segment is going to represent a sublimation or a deposition point. So a temperature and a pressure at which the solid can go from a solid to a gas, or from a gas to a liquid. So this is essentially separating the solid from the gas phase. Now at segment AD, these are going to correspond to temperatures and pressures that correspond to the melting or freezing conditions for that solid and liquid. So everything along that specific line is showing us separating the solid from the liquid. And then notice from A to B, this particular curve, this is separating the liquid and the gas phase. And so every point on that curve is going to correspond to the temperature and pressure conditions to either vaporize or condense the liquid and the gas. Now, a couple of other points that are mentioned here that you don't notice, the triple point is here in the middle. That's at point A. And then at point B, you have the critical point. So triple point at A is this point at which all three phases of matter are present. So you've got the solid, liquid, and gas phase that are there. And then at the critical point, that's going to correspond to your critical temperature and your critical pressure. So that's that point at which the liquid can no longer exist and it has to go into that gas phase. So again, triple point, that's when all three phases of matter are at equilibrium. And then the critical point, this is the highest temperature at which the liquid phase can exist. That's going to be your critical temperature and your critical pressure as well. Beyond that temperature and pressure, it's going to have to go into the gas phase. All right. Now, we're going to look at some other phase diagrams here. And so you're going to notice that we've got the phase diagrams of water versus the phase diagrams of carbon dioxide. And again, they have a lot of things that are in common. Notice that the pressures and temperatures are all very unique to each substance. But the one thing that I want to draw your attention to is I want to draw your attention to the segment that's separating the solid from the liquid phase from water, or from H2O and CO2. Now, the thing that you're going to notice about these phase diagrams is that the phase diagram for water shows that the liquid phase is going to exist at more temperatures and pressures than the solid phase, right? And that's telling you something about the intermolecular forces of attraction that are present there, right? It's telling you, obviously we know that water has hydrogen bonding, carbon dioxide has only London dispersion forces. Now, the other thing that this is going to communicate to us is that because that solid-liquid equilibrium line is sloped differently, notice that it's got a negative slope in water, but it's got a positive slope in carbon dioxide. This indicates that water expands when it freezes, and that makes sense, right? So liquid water, when it freezes, it expands, right? It can form an ice cube, and when that ice cube takes shape, it gets bigger. Whereas for carbon dioxide, when it freezes, it actually contracts. It gets smaller at the particle level. So just something to consider when you're looking at phase diagrams, just kind of a unique property to pay attention to when you're looking at phase diagrams. And again, what you might be asked to do when you're looking at a phase diagram is you might be given specific temperature and pressure conditions, and they might ask you what phase are you in, or if they give you specific conditions and they start changing the temperature, they might ask you what phase changes are occurring as you're increasing the temperature. So just keep that in the back of your mind. All right, let's take a look at characteristics of solids and gases, and then we'll be done with this particular video. So with solids, there are two general classifications for solids. There are going to be amorphous solids, which kind of from the word amorphous, it's going to have no form. So no pattern to the arrangement of the particles within the solid. Now, amorphous solids, when you start to look at their melting points, they're going to be over a wider range of temperatures. And so instead of it going directly into the liquid phase, like having an abrupt cutoff, what tends to happen is that the solid itself just tends to get softer and softer when it gets heated. So some things to consider that kind of fall in this amorphous category would be things like glass, plastics, and wax. Now, the second type of solid that we can talk about are crystalline solids. Now, your crystalline solids, they're going to have a much more well-ordered and defined arrangement of their atoms at the particle level. And in general, those crystals tend to have a repeated structure. And so because of that, the melting point is going to be in a much more narrow range of values for that particular substance, right? So you start thinking about metals, you think about water, or even diamond, for example. Those are substances that have a crystalline solid structure, and so then they get a more narrow range of temperatures at which they're changing from the solid to the liquid phase. Now let's take a look at crystalline solids specifically. Now, crystalline solids get broken down into 4 different categories, and you do need to know these different types of solids, specifically crystalline solids. So the first one is a molecular solid. And so from the name, it's formed from molecules, right? It's a molecular solid. Now, some characteristics of crystalline solids, they're usually soft, and they have a low melting point, and they generally have a relatively poor electrical conductivity. Now, a good example of a molecular solid would be something like carbon dioxide. If carbon dioxide is in the solid form, it's a molecular solid. We could even say that water is a molecular solid because it's made up of 2 nonmetals that are bonded together. That's what we mean when we say a molecular solid. Now, you could have what's called a covalent network solid. Big important piece here. Covalent network solids are formed from atoms, individual atoms, not molecules. So covalent network solids are very hard, they have very high melting points, and they generally have very poor electrical conductivity. An example of a covalent network solid would be something like diamond, because diamond is essentially a series of carbon atoms that are connected together. Now, diamond has a very high melting point, but it is not a very good electrical conductor. You've got ionic crystalline solids. These are going to be formed from ions, right? So these are going to be your ionic solids. They're hard, but they're brittle at the same time. That means that they can be broken into pieces. They generally have high melting points, but when they're in the solid phase, they have very poor electrical conductivity. And the last type of solid that we need to be aware of are metallic solids. And so your metallic crystalline solids are going to be formed from metal atoms. Now, depending on your metal, it could be soft or hard. That's not necessarily super important. They have high melting points. They have good electrical conductivity and heat conductivity. They're malleable and they're ductile. Malleable simply means they can be made into thin sheets, and ductile means they can be drawn into wire. Okay, so something that you guys are going to need to know how to do is if you're given a specific type of solid, can you classify it as molecular, covalent network, ionic, or metallic? And so hopefully kind of those parentheses definitions that are kind of listed there, so molecular formed from molecules, covalent network formed from individual atoms, ionic formed from ions, and metallic formed from metal atoms, can help you identify what type of crystalline solid you're dealing with. All right. Now, again, this is a table that comes from your textbook. And I do like this because it gives you kind of some things to consider. It gives you more of the properties, which I think you should familiarize yourself with. But the first thing it shows you, you should look at the form of unit particles that makes it up. It tells you what you need to be looking for, right? And then this table also gives us some examples of molecular, covalent network, ionic, and metallic solids, right? I won't spend time talking through all of this, but use this table to help you familiarize yourself with different types of crystalline solids. And just remember, metallic bonds are formed from metal nuclei floating in a sea of electrons. You should remember that from the previous unit, but just kind of as a quick reminder. All right, and here are some examples of some crystalline solids. So when I'm looking at each of these, you should be able to kind of recognize, all right, we got diamond and graphite. So those are all carbon atoms. That's a covalent network solid. The substance that we've got listed over here, that looks like a bunch of water molecules or something like that. So that's looking like our molecular solid. Here in this bottom left corner, those are ionic solids. And over here, this is a metallic solid. So covalent network, ionic, metallic, and molecular up in the top left. All right, let's talk about structure of solids. I'm going to be very quick here because we're going to get into things like unit cells that are not necessarily tested on the AP exam. This is really interesting if you want to learn more about like structures of solids. And so like material science would look at this type of stuff, but not a super important for us in AP Chem. So unit cell, this is the smallest repeating unit in a crystal structure. That's a unit cell. Now, a unit cell is the smallest unit with all the symmetry of the entire crystal. And so what we see is that the three-dimensional stacking of unit cells is what creates the crystal lattice structure that we're talking about. Okay, and so if you're looking at this particular diagram, the blue kind of slanted cube would be the individual unit cell, and the three-dimensional stacking of the unit cells is the crystal lattice structure that we see. Now, there are three types of unit cells. Again, this is not something that AP is going to be testing you on specifically, but it's just good to know and as you're moving forward, because you might see this later on if you take chemistry in college. So you've got primitive, which is simple cubic. That means atoms at the corners of a simple cube. So each atom is going to be shared by 8 unit cells. You've got a body-centered cubic, BCC. That means atoms at the corners of a cube plus 1 in the center of the body of the cube. So the corner atoms are shared by 8 unit cells, and the center atom is completely enclosed in 1 unit cell. And lastly, you've got the face-centered cubic, FCC. So you've got atoms at the corners of a cube plus 1 atom in the center of each face of the cube. All right. So a corner atom shared by 8 unit cells and face atoms shared by 2 unit cells. Now again, when we start taking thinking about what these look like. Not something you're going to be asked to do, but it is something that'd be good to note. Now, looking at those unit cells, your primitive cubic is up at the top. So notice that you've got atoms at each of the corners, total of 8 atoms. In your body-centered cubic, what you've got is you've got the 8 atoms that are at the corners, and then you've got another atom that's in the center. Now with your face-centered cubic unit cell, you've got your 8 atoms in the corner, and then you've got 2 atoms on the faces, right? All right, last thing when we look at properties, we're looking at gases, and then we'll be done with this particular video. When we talk about gases, just introducing some very quick properties here. Gases are highly compressible, and they expand to occupy the full volume of their container. So no matter how large the container is, no matter how many gas particles you have, the volume of a gas is going to be equivalent to the volume of the container it's in. Compressible means you can add pressure to them to cause the gases to move closer together. Now, when you have multiple gases in a container, they're always going to form what's called a homogeneous mixture or a solution with other gases. And just kind of a fact to kind of consider here, gases only occupy about 0.1% of the volume of their containers. Knowing that particular number is not important, but what I do think is of extreme value to you guys is to understand that the particles of a gas take up very little space when they're in a container as a whole, which is going to be important moving forward as we start to talk about other properties and other aspects of how gases behave, right? All right, so that's going to be the end of this particular video. That's going to end our topic of conversation as we've looked at solids, liquids, and gases. And so I hope this has been insightful. If you have any questions, please don't hesitate to ask in class or come to office hours to get additional help. I really appreciate you guys, and I look forward to seeing you guys again soon. Take care.